All right, let's take a look at another derivative application of optimization. A rectangular pen is to be built with 1,200 meters of fencing. The pen is to be divided into 3 parts using 2 parallel partitions. Find the maximum possible area of the pen. Okay, so assuming that the pen is completely surrounded. Okay, so in red I'm just going to include the fencing. And we also have the pen is divided into three parts using 2 parallel partitions. So let's assume that these are the 2 parallel partitions. And if you want to find the maximum possible area of the pen, what I'm going to do here is I'm going to let W represent the width, and I'm going to let L represent the length. So here we're going to have a length, here we're going to have a length. These 3 would be widths, these 4 would be widths, and therefore the sum of the total amount of fencing that you should see here is 4W plus 2L is equal to 1,200, right? We also want to look at an equation, well, specifically a function where we have A as a function of another variable. Now, A area is basically length times width, right? What you need to do is, if you want to create a function in order to find a derivative of the function, you need to make sure that there's only the function, what the dependent variable is only a function of one independent variable, not width and length, right? That would be two different independent variables, right? So what we could do is we could do substitution. So I'm going to call this equation 1, equation 2. In equation 1, what I want to do here is I'm going to divide all of my variables by 2. So I'm just going to divide equation 1 by 2. So you get 2W plus L is equal to 600. And we can see, and we can substitute, or we can isolate for a variable, L. So L is equal to 600 minus 2W. Now what I'm going to do here is I'm going to substitute that into equation 2. So area is now equal to, instead of L, I'm going to plug in 600 minus 2W times W. And the reason I did a substitution is now we can see that area is just a function of one variable, right? In this case, this is a relation, but now this is particularly a function. And because it's a function, we can write area as a function of width. And if you expand this guy out, I'm going to expand the W out, so you get 600W minus 2W squared. Okay, so area is now a function of width. So now because we have a function, we can actually optimize this by finding the first derivative. Okay, so if we want to find the maximum possible area of the pen and figure out the dimensions to create that maximum possible area, what I'm going to do here is I'm going to find the first derivative function, and I need to let the first derivative function equal 0. So the first derivative function a prime of w here is equal to 600 minus 4w. You're finding the derivative with respect to a change in width, and now that you have your derivative function, if I let this equal to 0, you get 600 minus 4w is equal to 0. I'm going to move the 600 to the other side. Negative 4w is equal to negative 600. And divide by negative 4 to both sides, right? So w is equal to 150. Okay, and in this case is 150 meters. So now we have w. So what that means is that if w is equal to 150 meters, or if the width is 150 meters, then we can maximize the area. Let's figure out what the length is when we do maximize this area, right? So we understand that according to equation 1, 4w, or 4 times the width plus 2 times the length, is equal to 1200. So we can understand that if w is 150, then 4 times 150 plus 2l is equal to 1200. 4 times 150 is 600, plus 2l is equal to 1200. 2l is equal to 600. L is equal to 300 meters, right? So therefore, the width and length are 150 meters and 300 meters respectively, and the maximum possible area is basically area is length times width. So we do 300 times 150, and we should get 45,000 meters squared. Okay, so that's how we can basically optimize area, right? By using the first derivative test.